All right, good morning, everyone. It's so great to see everyone here. My name is George Kantor. I am a research professor in the Field Robotics Center. I've been at Carnegie Mellon and in FRC for almost exactly 25 years. So I was hired as a postdoc, came in November of 1999. And in that time, I've built a lot of machines that have done very interesting things, and mostly have been just super fun to work on. You know, it's such a great area. I think we focus a lot on the work and the applications and the impact, but I think all of us are also here because it's fun. There is something about making machines do something difficult in a difficult environment that really excites people. So this panel is the future of outdoor autonomy. But before I get into the future, I just want to say a little bit about my own particular past, and I'll set up the other speakers who will move into talking more about the future. So, you know, this is the DepthX robot. It's an underwater vehicle that explored flooded caverns in Mexico. This was a project I worked on with David Wettergreen and some others, Bill Stone at Stone Aerospace. And the main idea of the project was we were in these underwater caverns in Mexico. They have these biomats on all the walls. The biologists didn't really understand how the biomats could survive because there's no light, no oxygen, those kinds of things. So the bottom line is they wanted to get down into these caves and get little plugs of sediment from the sides of these walls. To us, that meant we had to get this robot to build a map of a 3D underwater environment and then drive around into it without crashing into things, and then ultimately control itself to make contact with the wall and collect this sample. So those were the technical parts that we worked on, and I think the biggest technical innovation that came out of that was 3D SLAM. This was the first time we really had an application where we had to reason about the full 3D SLAM. We're using sonar sensors instead of cameras or lasers. And we did some things that were really exciting. This one has been talked about a lot, so I won't spend a lot of time on it. This is by far the biggest robot I've ever had the pleasure to be associated with. I was part of the AHS team that worked on this in sort of around circa 2010, and my role here was a positioning system for GPS-free navigation to fill in the gaps when the GPS might fail for various reasons. And it was a lot of fun, and working with a big group of people to do that was great. One thing I'll point out, I was just a couple of weeks ago, I happened to be in Chile, and I visited a mine where they had a fleet of 20 autonomous haul trucks, 3 shifts a day, just going. And we got to go out there and tromp around and look at them. And you know what? To the people there, it was no big deal. It was just a thing that did. It was a tool that was working reliably in their environment, and really rewarding to see that kind of thing. And that's what happens. These things start off as being exciting, fun, novel, and then they just become things that change the world. Driving, of course, we've heard a lot about, and it was one of the early applications in field robotics, because there was a time when really all we could do was drive, and driving was novel. And so, you know, going from the lessons of the DARPA challenge races to off-road autonomy and dealing with environments where the road might not be flat or you might not know what kind of vegetation to drive over. Very interesting. We did a lot of that. And then my main thing over the years became agriculture. And so Red talked about the deep, deep history that Carnegie Mellon Robotics, Field Robotics Center has in agriculture. You know, my first really deep dive into it was around 2008 when the USDA started the Specialty Crops Research Initiative. Carnegie Mellon won 2 out of, I think, 6 huge grants, and the 2 biggest ones, Tony was one of the other ones. I was on a team with Sanjeev. We suffered a lot of political backlash for that because there were a lot of entitled land-grant universities who thought that was their money, and when Carnegie Mellon came in and took a big chunk, there were some hurt feelings for sure. But I think that both of those teams did really well and showed that there's value in bringing people like us in, even though we weren't seen as ag people at the time. What did we do? That project, again, was driving, because driving was all we really could do. And we learned how to adapt the urban challenge things into these lower cost platforms that could navigate through nurseries and orchards and things like that. And that line of work has had many iterations over the years. This is a robot called Robotinist that was part of a robotic phenotyping platform. Around 2016, it was when we put this together. And I really like this picture because it shows all of the pieces, the past and the future of field robots for agriculture all in one place. It does drive, right? Driving is the past. We know how to drive now. Once we figured out how to drive, we had to learn how to bring value into these environments with sensing. And so that red camera hanging off the back is a sensor that can, in this particular case, do phenotyping. We adapted it into doing crop load estimation and things like that for specialty crops. That particular camera, my student Tim Mueller-Sim decided to spin off into a company called Bloomfield Robotics, which just recently was acquired by Kubota. So there is need for these things out there in the world, and you can build a market for them. And then the last part that's really easy to miss is if you look about halfway up the mast on that robot, there's a little simple robotic arm. And one of the people would laugh at me because I got super excited about this, but we on this project actually intentionally touched plants in an intelligent manipulation kind of way. And so that's the future, right? We started with the driving, we moved into the sensing and perception, and now the future is this intelligent manipulation, automating the things that have resisted automation because we don't have the mechanisms and the sensors and so forth to do that. But we're crossing that boundary. What does the future hold? Fortunately, you guys don't need me to tell you about that because we have this fantastic panel of researchers. Most of them are in their early career. All of them are in the Field Robotics Center, and they're going to be the ones who are casting the vision for the future and carrying it out. But I can give just a couple of hints why this is such. Whoop! Hang on. How do I? I don't know how to stop. Well, whatever. Sorry about that. These are some things that are enabling technologies that are going to drive the future and make this such an exciting era going forward. There are a lot of things that we struggled hard at back in the day to generate simple capabilities that you now almost get for free. The top left, platforms, right? We can get platforms today. We don't have to build our robots from scratch from the ground up. There are mobility platforms, there are manipulator platforms, and we can do proof of concepts of very interesting applications by putting these things together. It used to be, if you were going to build a real robot, especially one that was going to go outside, and you were writing a proposal for it, you put in $1.5 million just for the robot. Now, we put in maybe $100,000 if we want to do a good one, because we get so many components off the shelf. Top right, foundation models. I can't tell you how many hours and weeks and months and years of my life I spent doing perception tasks in complicated, cluttered environments. Now, Segment Anything does it all, or does a lot of it, right off the shelf. The bottom left is spatial modeling, and again, years and years spent reasoning in 3D, building 3D models. Now you can wave a cell phone around and upload the video to a website and generate this amazing, detailed 3D model. And then finally, on the bottom right is some of the things we're looking at in my lab right now, which is exploiting learning for demonstration. Now that we can bring these manipulators out in the field, we need to control them, and we want to do these very intricate manual tasks. And it turns out that right now, the best way to do it is to get people to do it and mimic the people. So there's some really great emerging technologies that are doing that. So with that said, I'm going to hand things over to the next speaker, who is Dr. Abhi Silwal. He's a systems scientist in FRC, just became a systems scientist this summer, though he's been here for several years working on a lot of these problems. And so take it away, Abhi.
So I guess to describe it, it goes without saying that robotics and AI have a lot of impact to make in agriculture, or rather is already doing that by providing ways to optimize crop production to feed this generation as with the next generation, at the same time dealing with complex situations created by shortage of farm workers in different industries within agriculture. So that's something that you typically hear in a talk that is related to agricultural robotics and showing robot systems, how they are built, how they work, what kind of promise and results are in the field. And I'm going to do the exact same thing, but at the same time, I also wanted to highlight some of the interesting research problem that agriculture brings to the research community as well. Particularly to manipulation, because it is such a hard problem. So to talk a little bit more about that, I wanted to show you these two videos. The video on the left-hand side, let's start it again. The video on the left-hand side is a multi-view registration of a grapevine, of a dormant season grapevine in field conditions. Dormant season meaning just the winter season where all the leaves have fallen off. And the person on the right-hand side is doing what we call as pruning, or just cutting off the excess vine, bringing it down to a specific size in preparation for the new upcoming season. So I just wanted to let you look at this video for a few seconds, and I'll come back and I'll walk you through as well what's happening and what's interesting about it. All right, so I will walk you through, but I also wanted to make a connection to robotics, that if a robot had to do this, what kind of capability that robot would need to be able to do this. So this person sitting in front of the vine uses both of his hands. In some cases, you will see him grab this flexible cane, bring in front of him, use another arm to go and make a cut. So that's dexterous manipulation. That's extremely hard in this kind of a cluttered environment. In some cases, you will see him lean deeper into the canopy, sort of have a deliberate contact between his arm, the tool, and parts of the vine, so that contact-rich manipulation becomes extremely hard problem to solve. And in some cases, he will just switch the tool from left-hand side to the right-hand side, and I even don't know how to do that with a robot system. So anyway, whatever he is doing here is extremely hard from a robotics standpoint of view, but also presents a lot of interesting challenges to robotics, and there are no existing robot systems that can do what he is able to do over here. Now, but pruning vines with robots is not completely impossible. So we have built robot systems that are autonomous in the nature that they can navigate themselves in front of the vine, but, and be able to prune them end to end. So this particular system navigates itself to a vine. It scans the vine very precisely, can make very precise models of the vine, and algorithmically we can point it to the location where it can go and execute those tasks. So we have shown this system, we have shown this autonomous system to work in field conditions. In an entire row, it was able to prune multiple vines from both sides of the canopy. However, we made a lot of assumptions for it to work, meaning these systems are only working in very simplified scenarios. Here, we had to use the machines to use the pre-pruning machines to make the vines much more simpler. So the working environment is much more simpler than the vine in its nature. But the most simplified parts are the intelligent part of the task, which is to figuring out where to make those cuts. And those where to make that cuts is what we call as pruning rules. And decades and decades of research have gone into sort of doing and finding a good way to say, here's how to prune a grapevine, or here's how to interact with the canopy. And then here, it's a very human-centric rule in the sense that these are designed for human beings. These are multiple steps, long horizon tasks that are really, really hard to encode in algorithms. So if it is such a human-centric rule, if it is hard to encode in algorithms, de facto way these days to get these kind of things done is through what George briefly touched base, something called as teach by demonstration kind of an approach, where if we could demonstrate these algorithms through expert demonstration to the robot, or rather an AI model, and hopefully that AI model captures all of that intricate detail that a person is doing. So that is based on the assumption that we have data available. However, that is a little bit tricky in agriculture because data in agriculture is a bit tricky, but it's much more trickier in this kind of situations where it requires a lot of skills to do those kind of things. So here we have 2 graduate students who are very diligently trying to teleoperate this robot to collect human demonstration data. If we wanted to do this with an expert farm worker, it would be hard to ask him to operate this robot and collect data for us, but it is actually much more harder to train graduate students and roboticists to do agricultural things at the efficiency of which farm workers are able to do. So collecting data is tricky. At the same time, it's outdoors, so weather plays a role. There are seasonal changes, and it's very, very likely that we will not be able to collect good data in time. So this is just teleoperation, which is not a new idea in robotics. There are newer methods. So this is John Kim, who is a PhD student in our lab, who has come up with his own version of see if this is play. But anyways, what is capturing, what this system does is that it takes the robot part away, the embodiment of the physical robot part away from the data collection process, where the only demonstration that is required is the in and out operation of this, just the tool end rather than the entire robot. So just by collecting the servoing action of going in and out of the canopy using these custom devices, we can actually train recent machine learning models, particularly diffusion-based methods, to actually learn from demonstrations and be able to replicate that in field conditions. So this is again training, collecting that data at scale in just half a day with about 200 to 300 demonstrations, training the policy overnight, and then deploying the robot in the field conditions just the next day. And it has some interesting behaviors, which is called as recovery behaviors, that if it misses a certain part of it, it knows that it has missed, it comes back again, it tries that again, and then it can do that over and over and over again without having to hard code anything, just learning from demonstrations. Now this is great, but there are lots of limitations, including the occlusion presented by the plant, but also all of these limitations that I mentioned about does exist, that if you don't get access to the field, if there are seasonal changes, if there are weathers, and if you can't make it to the field, you won't be able to collect data to train your models and then take it to the field and deploy them. So in order to not go through all of these limitations, simulation-based methods seems to be a really powerful method to do, and not just any simulation, but very, very what I would like to call as hyper-realistic simulation environment, where we can capture simulation of the field at a level with which we haven't been able to capture in the past. So this is Gaussian splatting-based representation, where this video over here shows the visual richness of the field at the level that we haven't been able to capture in the past. And the idea now is to make a hyper-realistic simulation environment by converting this visual representation into a simulator, do all the demonstrations and all the data collection inside of the simulation itself, and go from simulation to real field deployment in just one shot. So in order to make a simulator, there are a couple of ingredients that you need. You need the representation, which this splat model provides by itself. You need a robot and the object that is interacting with in that environment. Here, that task, again, these are 2 examples to start with. We had to figure out our own methods to embed robots into this newer representation, and then apply a few basic Newtonian physics to capture the interaction between the robot and the object here. When I mean physics, basically meaning simple things like gravity or friction or other things, and we can do data collection either through the teleoperation or through motion planners that are already existing in the simulator. And doing so seems to be very effective, that the input to the model or the policy essentially is just RGB information. There is not even depth information there. And simply by collecting all the demonstrations in the simulation or the synthetic data, we can actually go from simulation to real with almost 90%, closer to 90% efficacy. So that's the power of working with hyperrealistic simulation. And in order to take this into the field and be able to do all those interactive interactions with, for example, the vine pruning, what's missing here is the physics model of plant that are very plant specific, in the sense that how the robot is going to interact with the plant. That's the missing component here. So we're working on both first principles based method as well as learning based methods where you can capture that simulations. Once that is captured, it goes back to the pipeline, and in a few months' time, we are looking forward to deploying that full system in full autonomy, with full autonomy when it might have the capability to prune grapevines as close to what a person would be able to do. Sort of going towards the end of my talk, I wanted to talk some philosophical stuff here. In field robotics in general, we have this pipeline where we collect data. Out of that data, we make very simple simulation models of the environment, and using that simple simulation model, we test all of our algorithms, whether that is perception, motion planning, etc. And when it works, we graduate ourselves towards lab mock-ups where we test out in real system, but it's still in a lab condition, and then only when it works in the lab mock-up, we graduate ourselves towards real-world deployment, and we keep that in the loop until it works. So hopefully, with the methods that I just described, we could, in a way, start getting robots in the agricultural field much more sooner than what we've been able to do so far. So that's it. In sake of time, I just wanted to thank all the collaborators that I've worked with. Without their collaboration, none of this would have been possible. All the funding agencies that have sponsored this research, and the amazing people at Kantor Lab and Carnegie Mellon and the Robotics Institute. Without their support, none of this would have been possible. And there's more than that. What we have done, that's our lab. Please check this out. And thank you very much for your attention.
Take it away.
Thank you. Today I'm going to talk about a topic that is very exciting to me, which is flying robots in caves. And you might be asking yourself, why should I care about caves? Well, NASA has spent a decent amount of time and money trying to figure out whether we can establish human colonies inside of skylights or inside of lava tubes, which are essentially caves on the moon and Mars. So basically, when the planet, like the moon, was forming, there were these lava flows that occurred on the surface of the planet. The crust cooled, and the lava kept flowing underneath and created these tubes. And some of these tubes are could hold the entire city of Philadelphia. Another reason is there are multiple places in the world, like the Grand Canyon, where all the water, the source of the water, comes through caves. So monitoring that is important as climate change affects the water systems in our environment. We might also be able to synthesize new antibiotics from microbes found in caves. There's a line of research that is active looking into that. And finally, cave search and rescue is extremely challenging. So if we could have robots to help us out, then we could potentially save more people, not just in caves, but in other search and rescue domains. But why is this hard? Well, caves have really tight access. Some of them are gated. They contain tight passageways that are hard for people to get through. I don't think, if you're claustrophobic, I would not recommend going to a cave. Some of it is very tight. There are also vertical passages that have to be rappelled into, and the terrain is very complex. So what I've been working on is how could we create multi-robot autonomous systems that could just fly through caves at high speed and map them, and then transmit the maps back and the important information like, where there might be an injured person, fully autonomously. And that sort of vision aligns with the movie Prometheus, if you've ever seen it. But you might not know that there's a cave about an hour north of here, and it has the distinction of being the most dense cave in the world. It's about 40 kilometers of passage that fits into about 1 acre to 2 acres of land. It is quite scary. It's a maze cave, and you're on your belly the entire time. This is a picture of my friend on the left. He's actually sketching out the passageway on in a notebook. And on the right is the map that people have been working on for like 5 years. There have been 150 trips into this cave to create the map, all by hand. And these maps are encoded with terrain features like stalagmites and stalactites, where there are nice formations, elevation changes. So what if we could use robots to automate all of this? But there's still some challenges and opportunities for robotics in this context. So this is these are some pictures from a cave trip we did like maybe 3 weeks ago, and that's me in red. You can see just how complex the environment looks like. And when you go into these environments, you don't want to take a lot of stuff. So it might be hard to see, but I actually have a black backpack in the image on the left, and all of the stuff that I need fits in there. So we really need tiny robots and good interfaces and displays that are lightweight. You can just throw them into a bag and everything's robust. So it's resistant to particulates, mud, dust, and water. That's what we really need. But right now, we do have to take a decent amount of equipment into a cave, usually a laptop, the robot, maybe a router. So this could definitely be better. And for some context, I asked my grad students to put on a harness and get into a hole and map the inside. And it took a few people and a lot of rigging to be able to get them in and out. They did get out. But what if we could just throw some robots down there and have them map the passageway so I didn't have to put my grad students through this? In terms of algorithms, I think there's a lot of really interesting areas of research in anytime planning and mapping. We've been looking at how can you select the appropriate fidelity to model from underlying sensor data by balancing compute constraints and maximizing the fidelity of your model just on the fly using information theoretic techniques. There's also potential for advancing the state of the art in rapid navigation using learning-based techniques, resilience to uncertainty, and then the dream would be just having, someone who is not an engineer be able to take a bunch of robots out of their pocket and throw them in the environment and have them be small enough and lightweight enough that they could go anywhere, have them map the whole place and come back. We've also been looking at making robots more efficient. Right now we have to store all of the occupied and free space information. What if we could just get rid of all the free space information and just keep the data that matters around? Maybe then we could have smaller robots. Here's some results from some high-speed flights. Of course, everything has to be GPS denied when you go into a cave, but you have to be able to avoid obstacles and react very quickly. So this was a 5 meter a second flight. It's hard to see, so we slowed it down by 3x so you could see it avoiding an obstacle in real time without hitting it. And we also deployed our systems to forests. This is another high-speed flight. So ideally, we would have one system that could operate in diverse environments: forests, caves, buildings after a collapse, or even sewer systems, mines, anywhere. We don't really want to have to tune parameters. We don't have to send a team of engineers. Just the robots can go anywhere without having to have an expert on site. And finally, this is one of our cave experiments from about 3 weeks ago. And the robot navigates through the environment at high speed over a chasm that was about 10 feet deep using only vision-based navigation and an onboard IMU. So if you're interested in any of this, we have more information on our website, but the hope is that one day we'll be able to have a large number of small robots operating completely autonomously and being able to go anywhere. Thank you.
Yeah, so my name is Wenshan, and I became a faculty member last year, but I started here as postdoc 7 years ago. So recently, not recently, I've been spending 5 years on this off-road driving topic. But most people here have 50 or more years experience with it. I just want to share some of the insights or my view of how this, what is the key technology and what is the future going forward. So I think I don't have to mention the importance of this direction. So there are so many applications, but I do want to emphasize that it also brings a lot of interesting research questions. For example, the unstructuredness of this problem bring the normal SLAM planning control to a next level of difficulty. And also it prompting approaches that force an understanding of physical interaction. So why this is hard? So I use this example to show, so this is just a human teleoperating this vehicle in the off-road environment. Sorry, I have trouble playing this video. Let me see if it plays here. Not really. Okay, never mind. And so human has no problem navigating the complex environment like this, but you can see like human do a lot of like this unconscious analysis of a terrain. It's not about obstacle avoiding, not about classifying what kind of terrain it is. You really need to understand the interaction between robot and the environment in order to navigate through this very unstructured environment. So I want to emphasize that traversability is not about geometry. Sometimes tall grass is easy to navigate, but some more flat terrain like gravel is more dangerous and uncomfortable to drive on. Because of this unstructured, so we have less data, and a lot of times these data are very hard to label. So if you ask a human like how traversable this terrain is, it's really difficult to find a clear boundary between drivable and not drivable. And a lot of cases, we have a lot of auto-distribution situations, so we can never cover the whole distribution in your training set, even you have enough time and money. If you think about it, this is also a challenge for on-road driving as well. So if you live in Pittsburgh, you find a lot of these cases that have like long tail cases for self-driving. It kind of becomes off-road as you traverse on these bumpy terrain, and you're easy to stuck in some these paved but very bumpy road. finally, much of the difficulties in all types of robotics is trying to capture these long tail cases that aren't always covered in your training set. So the off-road domain really provides you a very good medium that you can tackle some of the problems that makes the robotics as a whole a very difficult problem. I want to share with you our work we did this year. So we trying to use self-supervised learning to remove the requirement of large data and rely on online adaptation to address the out-of-distribution situation. So we want to, in contrast to a lot of existing work that need a lot of human hand labeling and hand tuning, we are trying to use adaptation so that a robot can learn in the deployment time. So it can learn as it interacts with the environment. And so just a high-level overview of our system pipeline. So we still utilize the SLAM mapping algorithms to provide this top-down view maps. And a lot of the focus of this discussion is on the traversability estimation. So given this top-down view maps, how traversable the terrain is, then we'll utilize traditional MPPI planner to generate this trajectory to lead the robot to the goal. So the key question is, without a lot of label data, so how are we going to use this self-supervised signal, and where does this signal come from? And second question is, how can we do online adaptation efficiently and accurately? So overview of our system. So we have this full-scale ATV with a lot of sensors, including LiDAR, stereo camera, and drive-by-wire system. We have sensors on wheel to measure the rotation. We also have sensors on the suspension to measure the bumpiness. So to answer the first question, so we looked at a lot of proprioceptive sensors like IMU. So while we drive on road, human can feel like how safe, how comfortable it is. So the robot can do it as well. So we asked how does the robot feel, and use that signal as a supervision signal to figure out the traversability. So we looked at a lot of different signals, including the IMU acceleration and the robot pose. Like we will feel uncomfortable when we pitch and roll too much. And we also look at the control effort. If the trajectory is very hard to follow, if our execution results is out of expectation, so naturally we will have a very high cost. So as we traverse through all kinds of terrains, we know we collect these signals and we associate these signals with the terrain features so that we get an estimation of the traversability. The problem is this supervised signal is very sparse comparing to traditional human labeled data. And also it only covers where the robot can drive. So we have a lot of places like high obstacles. We never interact with where we won't have any label. So the high level solution for these two problems is that we really need a very good feature representation to deal with this lack of supervision problem. Once we already have a good feature representation, we can online just tune very small set of parameters, which doesn't require a lot of data. Also, the second thing is that we need a very reliable uncertainty estimation. So we are sure, like where we are not have enough data, and where we are unsure about. So coming to our pipeline, so we have this visual LiDAR mapping system produce this top-down view, RGB, and height map. From these maps, we extract very powerful visual features using nowadays foundation models. We try different foundation models, yeah, I think the Dino V2 provide us with very powerful feature representation, like without any fine-tuning or training. We project these features onto the top-down view frame, so that combining with some geometry features, they provide us with this good abstract feature representation about the terrain. On the other hand, utilize these proprioceptive signals. We know like how comfortable we drive on different types of terrain, so that we can make the prediction. So our prediction includes this cost map, a speed map, and the uncertainty prediction map. So just show some of the results here, the visualization here. So with our pipeline, so without any labeled data, we can identify those uncertain regions, like these objects we never see in our training set, like tires. Sometimes it's just some garbage in the terrain. Yeah, luckily. So you can see, so these objects are not seen before, but we can identify these objects and avoid them. Yeah, so with this online adaptation, we don't need any human labeling, but over a couple of seconds, we can already generate these cost map and the velocity map in higher and higher precision. You can see here the red is high cost, blue is low cost. The robot can learn like this trail in the middle generally has lower cost than the grass. Yeah, there's more example. Yeah, this is interesting case that we drive along the same trail for 2 laps. And in the first lap, everything is more conservative. On the grass area, you can see it's very high cost. But as we drive the second lap, we know that some grass area is safe to drive on. And also you can see the velocity, the average velocity also increased because the robot is more confident, like driving faster in those terrains. Yeah, here's just a more example, like you can also differentiate the gravel terrains without any human labeling. Yeah, so yeah, that's something I want to share today. In conclusion, I want to say this online adaptation and the use minimum data is another way, a very important direction to go. And we showed one example that we can rely on these adaptation methods to do self-driving in off-road challenging environments without human label. And combining this technology with offline training is an important direction to go. And we also want to develop a self-exploration algorithm that allow robot to explore and gain experience by itself. Yeah, thank you so much.
All right, so I'll tell you a little bit about planetary exploration and the work that we've done, but also what's upcoming. Okay, so this is going to jump all around. So for a little bit of history, up there in the upper left there, that's the robot that came to be known as Ambler, and that was started in 1987, so 35 years ago. Early work for NASA building concept vehicles and trying to advance the state of the art for planetary exploration. And you see a bunch of others from the decades after that. The Nomad robot in the center top there, which was first long distance traverse, autonomous discovery of a fossil in Chile. And a number of other vehicles that we've produced over the years, leading down to, in the bottom right, I'll talk about this at the end, that's the Moon Ranger vehicle that Red has been leading the development of that we hope to one day see on the moon. Okay, so planetary navigation, this is from more than 20 years ago now. Early work in trying to create vehicles that could operate in unknown environments, no prior knowledge, no GPS, natural terrain, obviously no roads there, and developing those techniques so that we could get our robots to drive around. So that's, as we've seen over the last day or so here, many examples of how that has advanced over the years. And just to give a little more context, this is just 5 years ago. The same ideas, the same algorithms that we were using for those planetary rovers then applied to off-road navigation, but the ideas of building models and then forward simulating the actions of the robot. Things have gotten more detailed, they've gotten a little faster with the processors and some of the other capabilities that we've added on top of that to do classification of the features in the terrain so that we can make better decisions about where to drive. But for the most part, this problem of getting from A to B, we have good solutions to that now. Of course, we have proof by existence of rovers on Mars and some rovers, not US rovers, but some rovers on the moon that are doing that type of exploration. So what's happening now and what's happening upcoming, that's what I think very exciting, and the thing that's kept me busy for the last number of years is now that our robots can get places, they can collect information, how can we make them true explorers? How can we embody some understanding of what they're looking for, what they're trying to investigate, give them some capability to make decisions about what measurements to make and where to go to make measurements that are relevant. So this idea of creating real science explorers where we take human scientists, because exploration is for us, right? And it's not very interesting if you send a robot somewhere it explores and never tells you what happened. So we have a person in the loop with their ideas of what they're trying to understand and maybe models that they've created, using that information to generate plans for, have the robot decide from that intent of the investigation where it should go, where it should take measurements, what information it could collect, and then assimilate that information to build a better model, maybe help explain the hypothesis that the scientists have, transmit that information, what's been discovered, what's the most useful, relevant information, how is the model improved, and then allow the scientists to refine the model, maybe come up with new questions, or maybe look for more evidence for their hypothesis, and then turn that into this virtuous cycle of robot and human working together to conduct some investigation, again, with the robot doing most of the work of collecting that information, refining it, modeling it, and transmitting it back to the scientist, effectively becoming better tools for our scientists to explore. So we've been working on that in the last few years, doing things like, I sort of compressed a whole bunch of different projects into one slide here, but the idea is that we're taking information from scientific instruments, not just cameras, but spectrometers and other devices. We're compressing that information, interpreting that information, and building models of the different, what those instruments tell us about the environment, so labeled here as feature maps, and then using those maps in a probabilistic sense to understand where are we confident about the measurements, where do we have unknowns, and from that decide where we should take more measurements and what instruments we should use for those measurements. We do that, and that enables the robot to decide a path, a plan of action, and reduce its uncertainty around the measurements it's making. And in this case here, we're trying to map the mineralogy of a site, so we're deploying a spectrometer and cameras. We're deciding where we understand the mineralogy and where we need to go next to take more data, and ultimately build up a mineral map automatically. And so we can give the command to the robot to explore this region and map the mineralogy and have it act for a long period of time autonomously until it's built up a sufficient model, or a sufficiently accurate model. So it's been pointed out before, we can come up with all these great ideas, but as roboticists, we really need to get out into the field to make sure that they work, validate the algorithms, test our results. So I'm not going to play this whole video at this point, but this is an example of a robot at a site in Cooperite, Nevada. It's very rich in a number of different minerals. It's building its interpretation of data from a spectrometer that it carries on board, encoding that in a Gaussian process model that is hypothesizing many different possible minerals at that site, and then using those predictions to refine this model of mineralogy, decide locations where it should sample next, and move forward. Let's see if I can skip ahead a little bit. So, you know, the idea then is that we use a measure of uncertainty to automatically decide where to go. And what you're seeing here is an example of a robot on the left-hand side that's sort of wandering around at random, and on the right-hand side, a deliberate path to best refine its information. And what we see is the reconstruction error, so our ability to accurately predict the correct signal from the sensors improves as the robot takes more samples along this deliberate path. So that allows our robot to intelligently select samples, but of course there's many other things that it needs to worry about. So another area of research is combining this information maximizing exploration strategy with all the other things that the robot needs to do, like in this case, avoid areas of deep shadow, avoid steep slopes and reduce its risk, and sort of deal with all these multiple objectives so it can not just explore, but do that safely, do that efficiently, and hopefully survive for long periods of time. So pulling in all the objectives, so now our explorer is able to survive for longer and longer missions. So those are some of the research things that we're working on now, creating these autonomous science rovers. Another exciting thing going on is actually taking some of these ideas and deploying them beyond Earth. So it's been a dream for, well, decades at this point. But upcoming, the recent work in lunar exploration. This is, you're seeing here, the Moon Ranger rover. So that's an actual robot. It's sitting in a clean room in the Gates building, funded by NASA as part of its commercial payload development program, with the first objective being to demonstrate fully autonomous navigation on the moon. So that type of continuous driving that Red showed a video of the old Rattler robot doing, or you saw our Zoe robot doing, driving continuously, kilometers in a lunar day, not just centimeters or tens of meters, but significant distances. And it goes back to those early robots. It goes back to that first video I showed you of building models. This is obviously in a smaller space in a sandbox here, but the models being built, this is sped up, I think, about 8 times, running on a single board processor, NVIDIA Jetson, building models of the terrain from stereo imagery from the cameras on board the robot, selecting a path, commanding that path, and executing. It goes around and around and around. Those red big circles are the goals it heads to one after another. But again, all of that work that we saw that took so many computers, so many processors, so many graduate students to build, now running on a simple embedded processor that we've put in this rover. That's going to be kind of dark, but last thing I wanted to show you is, and this goes to a number of the talks that we've heard, pointing out that simulation is really crucial to testing these systems. It's a nice looking video, but actually what's happening here is that this environment is generating stereo imagery and generating, or synthesizing IMU data. That information is being transmitted to our flight rover. It's sitting in a clean room. It's got the processor, the flight processor there, all the software running on the robot. That the algorithms are running, so it's doing the stereo mapping, it's doing the path generation, and then sending that command back to this visualization environment to see what happens. And we're able to run, tens of kilometers of tests in this this hardware in the loop simulation to validate that software and convince ourselves that, if and when we get this thing to the moon, it's not going to run into rocks. It's going to be able to travel those distances and reach some of the goals to achieve its second objective, which is to transport an instrument that measures the amount of hydrogen and, by proxy, the amount of ice under the ground. So that's what's happening now. And I guess I want to leave you with this one slide, the idea that future planetary rovers, you see on the top there, the Titan Dragonfly rover, and the bottom right there, one of the concepts for a Europa underwater explorer. These things are going to be not in communication. They'll need to act entirely on their own. They need to come up with their science objectives, come up with their plans and paths, and execute them, and then hopefully get back and give us information about these distant worlds. So with that, thank you. Thank you to many students over the last few decades, lots of great staff, collaborations with many of the faculty, and I guess since this is the Raj Reddy seminar, thank you to Raj for getting it all started.
No.
Thank you. I want to thank everybody, all the speakers, all the attendees for this wonderful symposium. We had some fantastic discussion and talks. And the one thing that it points to is that one of the things that we have not done well generally is to preserve our history and promote our history. So this symposium, like the previous ones that we had the previous years, thanks to Raj, were intended to do just that. So one of the things that we'll do is to follow up with all the material that were presented here and work with our colleagues in SCS and in the libraries, the robotics archive project, etc., to continue working on preserving and promoting that history. I want to just close with two things. Don't worry, I don't have a speech or slides. Do not be alarmed. I want to close with two things. The first one is on the slide, is to thank Raj again, not just for the opportunity to have this symposium, but for the opportunity for all of us to have to be able to do the work that was presented. So thank you, Raj. And the second thing is to thank Jenny and her team for putting all this together. Thank you. And Chuck Anthony. Okay.